All right, so here is an object on an inclined plane or a ramp, and I am going to continue to assume right now that we have no friction. Okay, so that means, just from everyday experience, if we put something on a ramp and it's really slippery, it's going to slide down the ramp, isn't it? And so that means we're going to have some, we're going to have some velocity and some acceleration down the ramp. And the question is, well, how do I handle this? How do I solve a problem like this? How do I find velocities and accelerations with a ramp problem? And why is the conversation about the normal force earlier important? Because it really is. Well, there's a couple little tricks that we need to do for these problems. And if you don't do these tricks, you can still do the problems, but they're just much more difficult to do. So one of the things we're going to do is pretend to take the free body diagram, and we're going to pretend to bring the free body diagram down to the ramp surface itself. And I'll bring this gravity over here. And when I do that, of course I can melt away the box because the dot represents the box. And I'm also going to, as I did before, represent my x and y axis along the ramp. So my x-axis, I'm going to call positive x down the ramp because I'm assuming motion is going to be down the ramp. And that means if the x-axis is on the ramp, the y-axis, which needs to be perpendicular to that, would be right along the normal force. And what that's going to do is put the normal force right along the y-axis, which is awesome. But it takes the gravitational force and it makes the gravitational force in the fourth quadrant. That means I have to break that up into components. Now, what a lot of students do to do this, they kind of say, oh, well, the gravitation acts along this triangle. And that's wrong. If you take this and you break up the gravitation into components, remember, components have to act along the x and the y direction. That would mean that the components have to be here and here. Because that would be a 90-degree angle along the y-axis and along the x-axis. And of course we need the direction of those. So we need to know that the gravitation is going to act this way and this way. So it's getting really messy, so I'm going to kind of try to erase as much of this as I can and redraw it. I did not want to erase my gravitation. So let's redo that in a better way. So we're going to draw gravitation, and this is FGY, because it's acting along the y direction, even though I have the y direction kind of tilted, and this is going to act along the x direction. And that's going to be FGX. So I now have gravitation in components, which we've never done before. Now, I'm also going to tell you through similar triangles, and you can believe me or not, but if you look at the similar triangles, if you're good at geometry, the angle of the ramp, that angle, the angle of the ramp here, is the same as the angle inside this triangle with the gravitation. But what's important to realize is that angle is, the angle of the ramp is the same as the angle from the y-axis to the gravitation. So this angle here is equal to, this angle here is equal to that angle there. Again, this angle of the ramp is the same as the angle in the gravitational component triangle, as long as you go from the y-axis, the negative y-axis, to the hypotenuse. If you go this direction, that's not obviously going to work. Okay? And you don't want this angle. That's not going to work. This angle and this angle are not the same. So that means that this here inside 36.9 degrees. I made this particular ramp 36.9 degrees again because the trig works. It's a 3, 4, 5 triangle basically. And so now I can determine a couple things. If I know that I had a 100 Newton mass, a mass that weighed 100 newtons, I can determine FGY and FGX. I can determine that, you know, if it's just a triangle and I use trig, FGX equals, now be careful, now look at the angle and look at the sides, look at opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse. So notice the x portion of this gravitation is related to the sine function. A lot of people get so caught up in like, oh, the x component's always the cosine. X component's always the cosine. That's true if you measure off of the x-axis, but we didn't measure off the x-axis. We measured off the y-axis. And so for ramp problems, this is going to be 100 times the sine of 36.9 degrees. And if I do that math, because of the 3, 4, 5 triangle, it'd be 0.6. Not sine. Well, back up. The sine of that would be 0.6. And so that's 60 newtons. And that means the y portion of the gravity is going to be related to cosine, because notice that is adjacent over the hypotenuse. Now remember, the hypotenuse is all of gravity itself, right? So, you know, if I want to know FGY, it's related to the adjacent side of the angle to the hypotenuse, because gravity is in the fourth quadrant. That is the hypotenuse. And again, a lot of students have a problem with that. They don't want to accept that, but it's true. And so FGY equals that 100 times the cosine of 36.9 degrees. And that's going to be 100 times 0.80, 0.8. That's 80 newtons. That should be an N.